Alright, hi, good day students. I hope that you are doing well. So now, as we have seen in our previous lecture, we have covered on 8.1 and 8.2. So in this pre-recorded lecture, as a part of our replacement class, I am going to cover on 8.3, which is elimination reaction of alkyl halides. So we are still on alkyl halides. So let me just ask you, can you guess what will be the product of elimination reactions of these alkyl halides? Okay, so don't tell me you didn't know. It is alien to you because we have covered the concept of elimination reactions in chapter 5. Okay, so basically, elimination reactions, we are going to produce alkene. Okay, so what are we going to cover in this part is first, we are going to talk the general features first, of course, the general one. Okay, and then we are going to look into the product of elimination reaction, which is the alkene. But for this one, I am not going to cover in detail because we have discussed about alkenes when we discussed chapter 6 on the hydrocarbons, correct? Okay. And then, when we talk about these elimination reactions, it's just similar to the substitution reaction that we have mechanisms that you need to know. So, the mechanism here, you need to understand that we have two types of mechanism, which is E2 mechanism and E1 mechanism. Okay, and finally, we are going to just cover a bit on the alkyne synthesis. Basically, it is from the alkyl halide become alkene and then become alkyne. So this one will just be in brief only because it is not very critical. Okay, so now let us proceed to the elimination reaction, which is the general features first. So I am not going to discuss this in detail. So as I said, elimination reaction, it will produce alkene. So it will proceed with the acid-base mechanism or acid-base reaction. So with regards to the acid-base or electrophile nucleophile reaction, we have also taught you in chapter 5. Okay, I hope you still remember this. Okay, if not, go through the module again. Okay, because it is already there. Okay, so now in elimination reactions, as it said, okay, elimination, okay, so we lost element, we eliminate some of the elements. So in this alkyl halide, what we eliminate, okay, and what we are going to form is we are going to form pi bond because we are forming alkene. Okay, so here the general elimination reaction, so this is it. Okay, so as you see, do you still remember about the alpha and beta carbon? You must. Okay, so the concept here, which one is alpha carbon? So this is our alpha carbon, right? Okay, and this is our beta carbon. Okay, alpha, beta. So remember, the X, okay, the alkyl halide, the halide is coming from the alpha carbon, and one beta hydrogen is going to be removed. Okay, so beta hydrogen is removed. Remember, do not try to remove the alpha hydrogen here. No, it is the one that is removed is the beta hydrogen. Okay, so it is going to react with base. Okay, so base. So basically, in this case, your alkyl halide is going to be the acid. Okay, so it is going to acid-base reaction. Now, what happened is that your beta hydrogen, it will combine, okay, it will be taken by the base, so it will go there. All right, okay, so they are going to combine like that. Okay, so what happened to the X? Okay, the X are going to leave. Okay, so X is what we call as the leaving group. So X are going to leave. So what happened is that you see that you have broken 2 pi bond. Okay, two sigma bond. Okay, so you are breaking this bond and this bond. So you are going to form a new pi bond. So this is the criteria of the elimination reaction. And you need to understand the pi bond will only form between alpha and beta carbon only. Okay, so this is the elimination reaction. Now, let us just have a look on the example of elimination reaction. Okay, of course, we don't want to rush into the mechanism yet, so let us look into how do you want to predict the product of elimination reactions. Okay, so now this is the alkyl halide, which is bromo 1, 2, 3, 4, 1 bromo butane. Okay, so when you look into the reactant, your alkyl halide, first of all, indicate which one is your alpha carbon, which one is your beta carbon. Okay, so this is your alpha carbon and this is your beta carbon. You see, so this is alpha and beta. So you see there is alpha hydrogen and beta hydrogen. The one that is being removed is beta hydrogen. You can take either this beta hydrogen or this beta hydrogen. So since this one we have seen, we want to remove this one, so yang ni tak payah. You don't need to care about it, okay? So leave it. Okay, so the one that will be removed is the Br, which is the leaving group, okay? And the hydrogen, which is the beta hydrogen. And you need to understand when they leave, okay, this bond will be broken and this bond will be broken. So where does the new bond, which is the pi bond, that will form? Okay, the pi bond will form between just now, this one between the alpha and beta carbon. Okay, alright, so, oopsie. Okay, so this is alpha and beta carbon, right? So you are going to form the pi bond between the alpha and beta carbon. Okay, so where does the hydrogen go? So you see, this is going to be your base, okay? So this is your base, K plus OCCH33. So this one we call it as potassium butoxide, okay? Third butoxide, okay? So this one, it's okay, you don't need to worry about the name of the butoxide there. We are going to learn it later. Okay, so this one, it is going to be the hydrogen, beta hydrogen here, it is going to combine with the base. You still remember in the general features. So you see, this is our hydrogen, okay? And just now, this is our base, okay? This is our base. When you talk about the base, when it comes to ionic compound, you just ignore the cation. Because you remember, when we dissolve the ionic compound, they are going to dissociate into potassium ion, which is the cation, and the anion, okay? So the anion is the one that is important, which is the base, okay? Alright, so now, what happened to the Br minus? Br minus is going to be, it is going to leave. So most possibly it is going to form KBr. But still, when they are ionic compound, they are going to stay as potassium ion and bromine ion. They are going to be cation and anion. They are separate, not stuck together. Alright? Okay, now, let us have a look at this one. Okay. This one is the cycloalkene, right? It is cycloalkyl halide. Okay, so this is our alpha carbon. This is beta carbon, or this is also beta carbon. Okay, so do you want to take this beta carbon or this beta carbon? No worry, because this is just going to be the same. So let us just take either one because they are the same. Okay, they are symmetrical. So let's just take this one. So this is going to be our beta hydrogen. So remember, one beta hydrogen is removed and also the halogen is removed. Okay, so the bond will form between the alpha and beta carbon. Okay, so the new pi bond will form between the alpha and beta carbon, as you can see from this product. Okay, so now this is your reagent, sodium sodium ethoxide. So this ethoxide, okay, we just want to take the anion because this ionic compound. Okay, so this one, this is sodium ethoxide. Okay, so it is going to combine. Alright, sorry, let me change the color. Okay, this one. Okay, so the OCH2CH3, it is going to take the hydrogen, you see, which is the beta hydrogen. Okay, now what happened to the Cl? Cl will be removed. Okay, sometimes in the question we can just give this one. We don't give you the sodium plus. Okay, that's not to worry, nothing to worry. You just leave the Cl minus as Cl minus. No need to write Na plus and Cl minus. Okay, all right. So next one. Okay, so do you also remember that from alkene, you talk about the addition reaction. From alkene, you form alkyl halide. That reaction, we call it as hydrohalogenation reaction. So, because you are adding the hydrogen and halogen, so hydrohalogenation. But in this case, you are removing the hydrogen and halogen. So, we call this elimination reaction. To be specific, we call it as dehydrohalogenation. D there meaning to say it is being removed, the removal of, okay? So this one is a beta elimination reaction. Why do we call it beta elimination reaction? Because as I said, remember, beta hydrogen is removed, okay? So as we talk about the just a bit of the mechanism, so you can see the curved arrow. Remember to use curved arrow, it shows the electron transfer. Okay, so if it is a full headed like this, meaning to say 2 electrons are being transferred. So the concept is going to be like this. Okay, all right, so this is the general one only. I will just talk about it generally. So this is B, okay, beta hydrogen, the base, sorry. Okay, so you have in the base, you have the 2 electron, correct? And these 2 electrons are being transferred to the hydrogen, okay? Meaning to say that this base is going to take the hydrogen. So this is why we call it as acid-base reaction, because this one, it attacks the hydrogen, okay? So what will happen is that there will be bond formed between the base and the hydrogen. So this is the electron, okay? So that's why it is this one, okay? So now what happened is that, okay, you are going to have the bond, because when you want to make bond between the hydrogen and a base, okay, this bond must be broken. So where does this bond will go? Okay, so let me put this in this color. Okay, so the 2 electron here is going to be transferred between the alpha carbon and beta carbon. So this is the one that is going to make the pi bond. So this is where it will reside. You see that, how the electrons are being transferred. Okay, so what happened is that when they want to form a new bond here between the carbon, alpha carbon and beta carbon, so you see this carbon, okay, it can only, remember, carbon can only have 4 bonds, right? So something must leave, okay? So the best one that can leave is the halogen. So because of that, that is why, okay, let us just put the electron. So the bond here is going to be broken, all right? So this one, the 2 electron is going to be transferred to the halogen. So that is why the halogen, it is going to have 2 extra electron, okay? So can you see where does the electron are being moved? Okay, so it is from the base here to the hydrogen. They make bond between H and B. All right, so what happened to the bond, okay, or the electron in the between the beta carbon and beta hydrogen here? They are going to be transferred as a pi bond, so it become pi bond here. All right, okay, so now when they want to make bond, remember carbon can only have 4 bond maximum. If it want to make bond here, then it must lose another bond. So these 2 bond here, which is made of 2 electrons, okay, they are going to be transferred to the halogen. So that is why the halogen gets the electrons, okay? So you are going to form the alkene. these are what we call as the byproducts. Okay, all right, so now when you talk about the bases, right, so here is the bases. Okay, so this is base, okay, and this one is base, this one is base. So what are the types of base that we can have? Okay, you can have, okay, you can have a different kind of base. Okay, so the most common bases used in elimination reactions are negatively charged oxygen compounds. For example, is the hydroxide ion. For example, you can add just like sodium hydroxide, potassium hydroxide, lithium hydroxide, okay, or any hydroxide ions, okay, as long as it is in the ion form. Okay, so or you can have the alkoxide, okay, the alkyl derivative. For example, it is still O, okay, O, okay, but it is attached to the alkyl group, okay. So OCH3, OCH2, CH3, OCCH3, okay. So all of this, if you see, when this one, they are all ionic compound. So we call them as the strong bases. When they are ionic compound, they are strong base, okay? When they are neutral compound, they mostly are what we call this, they are going to be weak bases. Okay, for example, you can also use water. Okay, all right, so to draw any product of dehydrohalogenation, so as I just taught you, you need to find the alpha carbon, identify the beta carbons, and remove the elements and etc. Okay, but you can produce constitutional isomer or different types of alkenes. Okay, so like this one, okay, so like this one, all right, so look at this. Okay, you have your where is it? Okay, wait, okay, so this is your alpha carbon. Okay, the carbon attached to it is what we call as the beta hydrogen, and beta carbon, and beta carbon. Attached to this beta carbon, we call it as the beta hydrogen. But as you can see, they are all CH3, CH3, CH3. So they are basically the same beta carbon. They are similar. Okay, so whether you want to form it this way, or if let's say I just want to show you, for the sake of showing you, we want to remove the hydrogen here. So you are going to form carbon double bond CH2, okay, CH3, CH3. So basically, this is just the same compound, okay? If you try to name it, they are just the same alkene, okay, which is propene. No, is it? 1, 2, 3. Okay, yeah, 2-methyl propene. Okay, all right. So however, you can also have more than one product. So later you need to determine, is it major product or minor product. Now, first of all, let us try to look into what will be the product and so on. Okay, so look at this one. Okay, so where is your what do we call this? Where is your alpha carbon? So this is your alpha carbon. Why this is alpha carbon? Because this is where our halogen is being attached to. So this is alpha carbon. So attached to the alpha carbon is what we call as the beta carbon. This is also beta carbon. But you see that these two beta carbon are different. So one I put beta 1, another one I put beta 2. Why? Because this one is CH3, okay, this one is CH3, this one is CH2, CH3, right? So they are different. Okay, so when we talk about the beta hydrogen, so let's say I remove the Br and this beta hydrogen. Okay, so this is beta. So the beta hydrogen from the beta carbon 2, okay, beta 2. Okay, so if I remove this one, meaning to say the bond will form between this, correct? Okay, between alpha and B2. So it is going to form this compound. Okay, what if I remove the hydrogen, the beta hydrogen, from the beta carbon 1 here. So I want to remove this one and the Br. So of course, in this case, the double bond will form between alpha carbon and beta carbon 1. Okay, so you are going to produce this product. As you see, this product, let's say product A and product B are different. So they are constitutional isomers. So which will actually we produce? Okay, we are going to look into that later. Okay, so all right, so this one I am not going to discuss this in detail because we have talked about the alkene. All right, so now when we talk about the product of dehydrohalogenation, you can either produce the monosubstituted, disubstituted, trisubstituted, tetrasubstituted, or the cis-alkene, or the cis and transalkene. Okay, so the key point in the dehydrohalogenation is that we are going to produce this one also I'm not going to discuss because we have discussed it. Okay, so we are going to produce different compound. Okay, so when we produce different compounds, so which one is a major, which one is minor? So for your information, I'm not going to discuss the product of dehydrohalogenation. I'm not going to discuss about alkenes again because we have discussed it in the previous topic. Okay, all right, so the point here, if you see, all right, the point here is that, okay, when you want to produce an alkene, the major product is going to be the one that is more stable. This is based on what we call as the Zaitsev Rule. Zaitsev Rule states that we are going to get an alkene that is more stable. So how do you determine the stability of the alkene? Remember, the higher the substituent, the more stable the alkene. The second one is that transalkene is going to be more stable than cis-alkene. Okay, so if you have a look at this one, okay, so let me just show you the product. Where is it? Okay. Is it? No, where is Zaitsev Rule? Where is it? Okay, reactivity. Okay, selectivity here. Okay, I will just introduce you this one first. Zaitsev Rule states that the major product of beta elimination reaction is the more stable product. Okay, so let us just try to look into the handouts here. So we are going to move into the alkenes. Okay, so the alkenes, alkyl halides. Okay, so alkyl halides. Okay. Alright, where is it? This is elimination reaction. So let us have a look at look at elimination reaction. Okay, look at this one. Okay, so elimination reactions of alkyl halide. Okay, so if you look at this one, it is at page 39. Okay, page 39. So if you have a look here, indicate the alpha and beta carbon. Okay, and then after that you draw the product. As I said, when you look into question that asks you for the mechanism and so on, do not be panicked. The first thing you need to do is identify the product, and if it can have major or minor, identify which one is major and minor. Do not panic. Predict the product first, only then you go with all the arrow things. Okay, at least you can get your product correct. Okay, so now let us look into this exercise. Okay, so where is our alpha carbon? So this, you see, this is our Cl, correct? So the carbon that is attached to it is what we call as the alpha carbon. Okay, so this is alpha carbon. All right, and then the carbon next to it, okay, the carbon attached to the alpha carbon is what we call as the beta carbon. So this is alpha carbon, this is beta carbon. All right, and then you need to understand on the beta carbon, here there is beta hydrogen which is being removed. Okay, so actually if you want to see, there is hydrogen here. Okay, so there's two hydrogen, but I will just show one. Okay, so the one that will be removed is this hydrogen and this Cl. Okay, so you are going to get this one. So what is going to be your product? It is alkene. So remember, the pi bond formed between alpha and beta carbon. Okay, so it is going to be like that. All right, okay, so this is going to be the product. It is the only product. Okay, so the only product. Okay, so what is this name? This one is 1-chloropropene. Okay, so what is the name of this product? This product name is propene. Okay, it is propene. Okay, I hope that you know how to name it. Okay, now let us look at this one. Okay, this one, where is your halogen? This one. So the carbon that holds the halogen is what we call as beta carbon. Okay, alpha carbon. Okay, so this is alpha carbon. So the one that is attached to the alpha carbon is what we call as beta carbon. So in this case, there is carbon here and there is carbon here. Can you see it? Okay, so this is what we call as beta carbon and this is beta carbon. If you look at this beta carbon is different because it is CH3 here. But beta carbon here, it is CH2 here because another one is attached to this CH3. So I'm going to name it as beta 1 and beta 2. Okay, so now it is time to try to draw the product. Okay, so what is going to be the product of this elimination? You need to do one by one. Okay, let us take at between the alpha carbon and beta 1, meaning to say the hydrogen that is attached to it is being removed and the Cl here is being removed. Okay, so all right, okay, so what are we going to have? We are going to have like this and like this because, okay, because this is your alpha carbon, this is your beta 1 carbon. So the bond will form between the alpha and beta 1, okay, or the bond can also form between alpha and beta 2. So you are going to have like this. Okay, and another one, you need to remember for this one, you need to check, does it have any cis and trans? The answer is yes. So you can also have like this. Okay, all right, so which one is going to be major product? Remember the Zaitsev rule. What does Zaitsev rule states that? Okay, the major product, okay, of beta elimination is the most stable alkene. Okay, so which one is the most stable between these three? So if you have a look, of course this one is the most stable because it is the trans 2 butene. Okay, it is trans 2 butene, okay, or trans but 2-ene. Therefore this one is going to be the major product. Okay, this cis butene is going to be the minor product. Okay, and this one is the minor product. It will be the least one produced. Why? Because this carbon, this alkene is the least substituted one. Okay, so next let us try to have a look at this one. Okay, so if you have a look at this one, now look at your fluorine, okay, your fluorine here. So where is your alpha carbon? Okay, so this is our alpha carbon. Okay, so this alpha carbon, so attached to the alpha carbon you have beta carbon. So you are going to have your beta carbon here, okay, which is attached to the alpha carbon. You can also have your beta carbon here, and also another one which is also beta carbon. Okay, look at this beta carbon. Are they the same types of beta carbon or not? Okay, so look at this. Okay, look at this one. Okay, beta here is beta 1 because this one is CH2. Okay, but if you look at this one and this one is CH3, this one is CH3 as well. So they are the same type of carbon. So beta 2, beta 2. So how many types of product you are going to have is that you are going to have 2 constitutional isomer. Only 2. Why not 3? Because they are the same. I will show you. Okay, let us have a look at if we form bond between alpha and beta 1. The one that is being removed is the hydrogen from the beta 1 and the fluorine from the carbon alpha. Okay, so now the product is going to be like this. Okay, like this. Okay, so that's it. Okay, so is it going to have any cis or trans? The answer is no, because okay, there is no stereoisomer here. I hope that is clear for you, because you should know by now. Okay, now let us have a look at between alpha and beta 2 here. So the product is going to be like this, correct? Okay, if you want to try, you can look at this alpha and this beta 2. Okay, this alpha and beta 2. Okay, now if you look at, okay, this alkene and this alkene, they are basically the same, correct or not? Okay, they are basically the same, right? If you try to name them, it is the same because they are the same compound. So that is why you are going to produce only 2 products. Okay, so between these 2 products, which one is going to be the major, which one is going to be minor product? So the answer is that this one is going to be the major product because it is more stable. Why it is more stable? Because it have more substituent on the carbon, okay, on the carbon here, okay, carbon double bond. So carbon double bond, you have 1 substituent, 2 substituent, 3 substituent of R. Okay, but if you look at between this carbon, okay, you only have 2, which is 1 and 2, correct? So this one is going to be the minor product. Okay, all right, so that's okay, that's it. Okay, so let me just try to check to you. Okay, this might be a bit tricky. So now look at this one. Which one is your alpha carbon? Which one is your beta carbon? First of all, this is your halogen. So where is your alpha carbon? It is here. Okay, so this is going to be the alpha carbon. So where is your beta carbon? So your beta carbon is this one and this one. Okay, so of course, if you look at this carbon and this carbon, this one is going to be beta 1, this is going to be beta 2 because they are different types of carbon. Okay, all right, so however, when you want to produce a product, is it possible that you make bond between alpha and beta 1? What do you think? Okay, the answer is no, not possible. You cannot make bond between alpha and beta 1. Why? Because at beta 1 here, you do not have any beta hydrogen. Okay, let me just show you. There is carbon here. But this carbon is attached to the alpha carbon, attached to this carbon, attached to this carbon, and this carbon. So you see, there's already 4 bonds here. So there is no hydrogen going out of this carbon. So therefore, you cannot form product between alpha and beta 1 because there is no beta hydrogen. Remember, if you want to form bond, you need to form bond between the alpha and beta, and that beta must remove the beta hydrogen. Okay, so but at this beta 2 you have hydrogen, hydrogen, and hydrogen. Okay, so it is possible. So this one you only have one type of product, okay, which is this one. Okay, so this is going to be the only product. Does it have any stereoisomer? The answer is no. Okay, so does it have any like the cis and trans? No, the answer is no. So how do you determine that? Okay, you just look into the hydrogen there. Okay, so because this one they have the hydrogen, okay, these two at the end they have both hydrogen. Okay, so I'm not going to discuss that in detail. Okay, so for all of this, you can try this on your own. Okay, you can try it on your own. Okay, for your information, let me just give you some hints. This one, it will have 3 products. Okay, why? Because this is our alpha carbon. Okay, so this is alpha carbon. So where is your beta carbon? This is beta carbon, beta carbon, beta carbon. Okay, so this beta carbon, and beta carbon, they are different. Okay, this beta 1, beta 2, beta 3. So let me try to draw this for you. Is it going to be the same or not? So between alpha and beta 1, it is going to be like this. Okay, now between alpha and beta 2, okay, between alpha and beta 2, you are going to form like this. Okay, next, between alpha and beta 3, you are going to form this kind of product. Okay, so are they the same? No. When you try to name them, they are different. Okay, this one and this one, they are different. Okay, so if you try to name them, they are different, so they are constitutional isomer. Okay, so which one is going to be the major product? Okay, so the major product is going to be, okay, there are 2. So this one is the major product, this one is the major product as well. Okay, so this is the minor product. Why? Because around this carbon, okay, the one that is attached to it, how many substituent? 1, 2, 3. Okay, this one also 1, 2, 3. Okay, so you have 2 major products there. Okay, so you can try out for the next one. Okay, I am going to proceed with the mechanism. Okay, so now when we want to talk about the mechanism for the elimination reactions, okay, so when we talk about the mechanism, you can see you can have 2 types of mechanism, just like substitution reaction. You can have SN1 and SN2. For elimination reaction, you can have E2 and E1. Okay, so remember, 2 meaning to say bimolecular elimination, meaning to say this reaction have the second order reaction. You do not you cannot think that, oh, if E2 meaning to say it have 2 steps. No, it doesn't work like that. E2 meaning to say bimolecular elimination, meaning to say the reaction involve only 1 step. Okay, no worry. We are going to look into it one by one. Okay, the difference is that, okay, the E2 and E1 mechanism, they differ in the timing of the bond formation, okay, or the bond breaking. Okay, so the concept, if you can understand the nucleophilic substitution, okay, the SN1 and SN2, it is going to be easy for you to understand E1 and E2, because some features are in common. That is why I said, okay, organic chemistry, not all of it is about memorizing. It is about understanding. You have to understand. If you understand, you will say that, oh, everything are just the same pattern. Okay? Alright, so now let us proceed with the mechanism. So first of all, we are going to look into the E2 mechanism because this is much simpler because it is just one-step reactions. Okay, so the most common dehydrohalogenation mechanism is the E2 mechanism, but you cannot say that, oh, must be E2. Okay, sometimes we can also ask for E1 mechanism. Okay, so when we talk about E2, SN2, what does it mean? Meaning to say this reaction exhibits second order kinetics. Okay, so second order meaning to say both the alkyl halide and the base appear in the rate equation. Do you still remember about the rate of reactions? Okay, when we have a rate law, okay, it is going to be rate equals to K, the reactants and the other reactants. So it is the reactant, the order is 1 here, the order is 1 here. So because of that, okay, this is overall a second order reactions. Okay, so meaning to say this reaction is concerted or it is in one step only. It occurs in a single step. Okay, so let us have a look at the example. Okay, this is the simplest one. Okay, so this is a 2-methyl-2-bromo-propane. Okay, so as I said, first of all, when you want to have this kind of question on mechanism, predict the product first. Okay, predict the product first, only then you think of the what is going to be the mechanism, how does the reaction goes, and so on. Okay, so first of all, this is going to be your alkyl halide. So meaning to say this is your alpha carbon. So attached to the alpha carbon is the beta, beta, and beta. But all these beta carbon are similar. So you can just take at any beta carbon. So I'll pick up this carbon. So this carbon, okay, it have a beta hydrogen. So you need to draw out the beta hydrogen. You need to show it because later we are going to show mechanism. So now this is our alpha carbon, beta carbon. So we are going to remove what? We are going to remove the hydrogen and Br. Okay, so your product, you should get something like this: CH2, CH3, CH3. Correct? Okay, because remember, pi bond formed between alpha and beta carbon. Okay, so now once you have predict or identify what could be the product, now let us look at the mechanism step by step. Okay, so first of all, okay, all right, here, so alpha and beta carbon. So this is your beta hydrogen. Okay, so how does the reaction is going to proceed? As I said, first of all, the reaction will react with the base. This is acid-base reaction. So the base here is OH, okay? The base here is OH. So OH here, actually, it have a 3 lone pair. It depends on you. If you want to draw the lone pair, you can. If not, you can just pull the arrow coming from the negative charge because that negative charge indicates the lone pair. That is fine as well. That depends on you. So for me, I like to draw the lone pair. So I will draw the lone pair. Okay, so this is the lone pair. Okay, so the first step, what will happen is that, okay, there will be what do we call this? Okay, I will pull the arrow. Okay, there will be a transfer of electron because the arrow here coming from the negative, but I want to show using the lone pair because I like to show with lone pair. Okay, so the curved arrow will attack the hydrogen. Okay, so you see there will be form a bond between oxygen and hydrogen first. Okay, So you will expect it is going to produce H2O. Why? Because initially it is OH like this, correct? Okay. Alright. So now these two electrons are being used to make bond with hydrogen. So what will happen is that, okay, so you are going to form this with the hydrogen. So it is going to be a water. Okay. Alright. So now when this hydrogen it want to stay with the OH, it must leave, okay, the carbon. Okay, so what will happen? Okay, so what will happen? The bond between the carbon and hydrogen, which contains two electrons, will be broken. So when it breaks, okay, these two electrons will be transferred to the carbon, between the alpha carbon and beta carbon, to make a pi bond. This is how alkene form. So that is why you form a pi bond here. Okay. So next, if you want to form bond here, the alpha carbon here, it can only take 4 bonds. So that is why something must leave. The one that will be leaving is going to be the Br. Okay, so let's say you have 2 electrons here, because you do. Okay, so you are going to transfer these 2 electrons to the Br. Okay, so that's why on the Br here you have the 2 pair of electrons. That's why it is with the negative charge. Okay, can you see it? Okay, so now you can see this is the steps of the reaction to produce your alkene and also the byproducts. Okay, I hope that it is clear for you on how the mechanism goes. Okay, so next is that I am going to look into the energy diagram for the E2 mechanism, because this reaction is one step, so you are just going to see the energy diagram to be like this. Okay, the energy diagram is going to be like that. Okay, and this reaction is usually exothermic unless it is stated otherwise. Okay, so the reaction is simple, so you just need to, from what you draw here, okay, so this is going to be your reactant, this is going to be your product. Okay, make sure that you know what is the activation energy. So this is activation energy. Okay, so and this is going to be the transition state that you must be able to draw. So why do we have all this dot dot dot? Why? Because there is a bond about to form between the hydrogen and OH, hydroxyl, okay, hydroxide ion, and there is hydrogen bond that is about to break between the carbon and hydrogen there, and this one, it will be transferred, so it is about to form a pi bond. So, and at the same time as well, there is bond that is about to break between carbon and bromine. Okay, so that is how you draw. When you draw a transition state, okay, you need to consider all the arrows. You see, if you have 3 arrows here, meaning to say should be you have the what do we call this? Okay, you should have all this what do we call this? All this bond that is about to form, about to break. Okay, it is being shown there. Okay, all right. So drawing energy diagram is important. Okay, so I hope that you take note on that. Okay, so when we talk about the reagent for ES2 versus SN2, okay, this one I would say it is not really critical when it comes to your level. At foundation level, okay, we will mention, consider the substitution reaction below, consider the elimination reaction below. So you don't need to think, okay, when we react this, is it going to go with elimination or substitution? So you don't need to worry much. So you can read through this slide if you want, but I would say this is not going to be really critical for your level. Okay, so I will skip this part. Okay, now in terms of the reactivity of E2 mechanism, okay, we are going to look into the types of alkyl halide, okay, and also the types of the halogen or the leaving group, okay. And maybe on the effect of solvent, I will not discuss it, okay. It is not really critical for you. Okay, so the one that is important is especially on the effect of the types of alkyl halide. So what happened is that, okay, in E2 mechanism, okay, if you increase the R groups on the carbon with the leaving group, meaning to say you are increasing the number of beta carbon, how many beta carbon you have, okay, then you are going to form a more highly substituted, okay, or more stable alkene, okay. So if we produce a more stable alkene, okay, then the reaction is going to be more reactive because you are producing something more stable, so the reaction is going to be faster, okay. So in the reaction, since the disubstituted alkene is more stable, the tertiary alkyl halide reacts faster than primary alkyl halide. So look at these types of alkyl halide. Look at this carbon. This is your alpha carbon. Alpha carbon here is attached to the one beta carbon only, okay. But if you look at the second one here, this is your carbon, okay. So your alpha carbon is here, okay, and your beta carbon, and beta carbon. You see, you have 3 carbons, so meaning to say this is tertiary alkyl halide. So which one is faster, the primary or tertiary? Because when you have primary, you are going to form, and when you have a tertiary alkyl halide here, you are going to form a more stable alkene. So this reaction is going to be more reactive. Okay, I hope you pay attention to this. This is going to be important. Okay, so next is that on the effect of leaving group. So what if you substitute the bromine with the fluorine, or with fluorine with the chlorine, or the chlorine with the iodine, and so on? So what happened is that, okay, it will depend on the types, okay, or the easiness of the leaving group ability. So for your information, okay, this one we have discussed in substitution reaction. So which one is the leaving group ability? So the one that will easier to leave is the one that is bigger, okay. So the iodine is going to be easier to leave, okay, and be more stable on its own. So if you change it from going down the group, okay, so the rate of reaction is going to be faster. The reaction is going to be faster. The rate of reaction is going to be higher, okay. Okay, so effect of solvent, I'm not going to discuss it, okay. And then this one on the selectivity, I have discussed it earlier. We call this as Zaitsev Rule. So this reaction, E2 mechanism, is a regioselective. What is regioselective? Meaning to say it is selective towards one type of constitutional isomer, okay. But if you look at the mechanism on the SN2, it is what we call as stereoselective, because it is selective towards one type of stereoisomer. So here it is more on the regioselective, on constitutional isomer. Okay, how do you pick the major product? Okay, so that's it. Okay, so that's it on the E2 mechanism. So what is best is if we can do exercises. Okay, so let us try and look into the exercises here. Okay, this is a reaction. I have specified this is E2 reaction, which of course, if in exam, okay, we are not going to tell you that this is E2, because you need to think this on your own, okay? So how do I know that this is E2 reaction? Because I react it with a strong base, which is an ionic compound. If you look at this one, okay, the base here is going to be favored by strong base. So if you look something, okay, when it comes to elimination reaction, doesn't matter what kind of what do we call this, types is it, okay? So here, like here, okay, when it is secondary, okay, you can go with strong or weak base. Okay, first of all, look at this type. Okay, so in this case, this is a secondary alkyl halide. Okay, so secondary alkyl halide, so it is secondary. So the base is strong base because I use ionic compound. So it is going to go with E2 mechanism. This one you need to understand. When you understand, you are going to see it clearly, easy for you to predict. Okay, because as I said in exam, of course, we are not going to tell you this is E2 mechanism. Okay, you need to think on your own. Okay, so this one is strong. So that is why it is E2 mechanism. Okay, so first of all, as I said, before you go with the mechanism, the steps, and so on, why not we predict the product first? Predict the product first, okay? So the product is going to form between alpha and also the beta carbon, correct? Okay, so which one is going to be the major product and minor product? Okay, so it is going to be like this. Okay, so this is going to be the major product. Okay, actually for this one I have discussed with you here. Okay, it's just similar, so they are going to form. So for this one, I'm not going to draw for all. We are going to just draw for the major product, okay? Because for minor product, okay, the steps are similar. It's just that you are attacking different beta hydrogen, okay? So now, when you want to draw the mechanism, what do you do? Okay, so first of all, okay, draw it first, okay? So you are going to remove the the beta hydrogen, which is at this carbon. Okay, must be at this carbon because you want to form the bond here. That's why it is important that you predict the product first. Okay, so you are going to have this one. So you are going to remove the beta hydrogen. So it is best if you can show the beta hydrogen. So I will just show one of it. Actually, there are two beta hydrogen there, but you don't need to show all because the one that you want to remove, only one here and one here, correct? Because you are going to remove this one and remove this one to form this product, correct? Okay, so no need to draw all. Okay, and then when you have like this NaOH, you do not draw them all. Remember, when they are dissolved, okay, they are going to dissociate into sodium ion and OH minus ion. So the one that we are going to use is only the hydroxide ion. So OH, okay, so the OH. So for me, as I said, I like to use the lone pair, okay? It's just my preference to use the lone pair. If you want to straight away use from the what do we call this, from this charge, also not a problem. Okay, so first step, okay, I'm just going to use this one. So first step is the attack of the base to the hydrogen, okay? So the hydroxide ion is going to form bond between the between the oxygen and hydrogen. So it is going to form HOH, which is a water. You can just write H2O. Okay, next is that what is going to happen, there are two electron here, pair of electron between the beta carbon and the beta hydrogen, and this is going to go to form pi bond between the alpha and beta carbon. And now if it wants to form the pi bond, okay, you see the alpha carbon here, it can only have maximum of 4 bonds. Therefore, something must leave. So the bond between the alpha carbon, and also the bromine here is going to be broken by transferring the electron to the Br. So you see the Br, the alpha here, they are being broken. So you are going to form Br minus. Okay, so the two electrons are being transferred there. So actually there are like 3 pairs of lone pairs. So if you want to draw, you can. If you don't, also I understand. Okay, and your main product here is going to be this one. Okay, so I will just copy. Okay, so I will just copy this one. So I will just paste it here. Okay, so that is how you draw the E2 mechanism. So now, how does the energy diagram will look like for this reaction to produce the major product only? In the case that the question asks you draw for the minor product, then you have to draw the mechanism for the minor product. Okay, it depends. So here I just show you for the major product only. Okay, so for the energy diagram, remember, how do you draw energy diagram? Because this reaction is a one-step reaction. So one step, energy here, time or coordinate here, depend. You can write time or coordinate, depend on you. So this reaction, most of the time I say it exothermic. Unless we state it endothermic, then you should know. Okay, so here it should be your reactant. So here your reactant, so will be like this, okay, and also OH, or you can write the sodium hydroxide. So the product is going to be this one, okay, plus H2O, okay, plus Br minus. Okay, then you are going to label your activation energy. So activation energy is going to be here, okay, and then you can also label your delta H. All right, okay, so now what is going to be here? It is going to be the transition state. So how does the transition state looks like? Okay, so when in the mechanism steps, okay, so what will happen? You are going to have this one. So it is like this, correct? Okay, so what you have is that you have your hydrogen, and this bond is about to first of all, let us just draw it first, Br and also the OH. Okay, remember, based on this bond, okay, this mechanism, so this bond is about to form, okay, and then you have this bond about to break, and the pi bond is about to form, and the bond between carbon and Br here is about to break. Okay, so that's how you need to draw it. Okay, so then you close it with a double dagger. Okay, so that is for the energy diagram and also the reaction mechanism. So next is that we are going to proceed with E1 mechanism. Okay, now the E1 mechanism, the dehydrohalogenation of the CH3Cl with water can form the alkene, and it can be used to illustrate the second general mechanism, which is the E1 mechanism. Apart from the E2 mechanism, you can also have E1 mechanism. So why we call it E1? Why 1? Because it is first order kinetics. So first order, the one that is only involved in the rate law is only the alkyl halide. Okay, so it is E1 reaction. It is going to have 2 steps. Okay, so just like the SN2, so we are going to look into it one by one. Okay, so we say there are 2 steps. So what are the 2 steps? You need to show one by one, right? Okay, so the first step is just like this. You remember the addition reaction, it forms the carbocation. So this one, carbocation. Okay, so there is a carbon here. So this is your wheat. Okay, so this is our alpha carbon. Okay, so the alpha carbon, the first step is that, okay, this one is going to be, it is going to form carbocation. So the carbocation form at the alpha carbon. Okay, so this one, okay, this one, there is bond between carbon and iodine. This carbon and iodine, between them, they have 2 electrons. So the 2 electrons here is going to be transferred to the I. Okay, so the iodine here, okay, you have the extra 2 electron pair. Actually, you already have 3 here. Okay, so actually you have 3. Okay, like that. So now it becomes I minus. Okay, and it forms carbocation. Remember, the first step, the goal is going to form a carbocation as the intermediate. Okay, so that is why it is going to be like this. Okay, so this is your carbon, this is your alpha carbon. Just now it have become the carbocation. Okay, so this step is a slow step. It is the rate determining step. So that is why the rate law, it will only involve the this reactant, okay, the alkyl halide alone. Okay, so now the CH bond is cleaved and pi bond is formed in the second part. Okay, so in the step 2, what is going to form is that, okay, usually when it comes to E1 mechanism, we will use weak base such as water, because water, it is a neutral compound, so it is a weak base. So on the water, okay, so usually when it comes to water, I like to draw the complete structure. For example, wait, like this. Okay, like this. Oopsie. Okay, oxygen, okay, hydrogen, hydrogen. Okay, and then on this you have 1, 2, 3, 4. Usually I like to draw it like that better. Okay, because in this case I just want to show you, correct? Okay, so the 2 electrons, okay, the 2 electrons are being transferred to the hydrogen here because it wants to form bond with the hydrogen. So in this case, it is going to form a H3O plus, because you have like H, okay, sorry. Alright, sorry. Okay, so it is going to form HOH, and the bond like this, and this one formed with the hydrogen here. Okay, this is the new hydrogen, which is this one. Okay, so it's like there. Okay, so now the bond here, okay, now if the hydrogen want to make bond with the H2O, it must break the bond between the carbon and hydrogen. So what happened is that there is 2 electrons actually, right, in the bond. So what happened, so I'll just draw it as a line there. So what will happen is that there, it is going to be transferred between alpha and beta carbon, which is the carbocation and also the beta carbon. So in this case, it will straight away form the product, okay, which is this one. It have a pi bond. So why don't you have another step? Because you already removed the halogen initially, okay, earlier part you have removed it. Okay, all right, so now what is going to be the energy diagram for E1 mechanism? Because this reaction is a 2-step reaction. So when it is 2-step reaction, it is going to have an intermediate. Okay, the intermediate is going to be the carbocation. So this is the heel for step 1. This is the heel for step 2. Okay, so here it is going to be the heel for the step 1. Okay, so now look at the step 1. What is the reactant? Okay, so what is the reactant? What is the product? So you draw it there. Okay, so next, okay, if you want to look into what is going to be the transition state, so you look at the transition state. is that you are going to have a bond that is about to break between the carbon and iodine. So this is going to be your transition state. Okay, so iodine here. Okay, next in the second step, okay, the second step is this one. Okay, so the second step is this one. Okay, so as you can see, all right, this reaction, okay, the second step, okay, so for this reaction, the second step is this one is the reactant, this is the product. Okay, so what are you going to write is it is going to be like this. Okay, so see this one, the bond between the water and hydrogen is about to form, and the bond between carbon and hydrogen is about to break, and the bond between the carbon and carbon, which is the new pi bond, is about to form. So this is going to be the transition state. Okay, so that's it. Okay, now I am going to move on to the reactivity of E1 mechanism. So the reactivity of E1 mechanism is that you are going to have for the types of alkyl halide, the strength of base, and that's it. Okay, so for the types of alkyl halide, the trend, it is a bit different if you compare SN1 and SN2, but E1 and E2, they have the same trend. They will favor the tertiary alkyl halide. Okay, the more the substituent, the higher the stability. Okay, so why does the E1 reaction will favor a higher like tertiary alkyl halide? Why? Because it is going to form a carbocation, and this carbocation is going to be more stable. It is going to be more stable when there is more substituent or the R group. Okay, so this is a carbocation stability. So that is why if E1 reaction also, we will favor the tertiary alkyl halide. So in terms of the strength of base, remember, if you have a weak base, okay, weaker base like water and also like alcohol will favor the E1 reaction. So in terms of the Zaitsev Rule, similar. The Zaitsev Rule is also applied in E1 mechanism. So if you can see, if it is weak base, we are going to favor the E1 mechanism. So now, do you want to know, is it going to go with E2 or is it going to go with E1? So later we are going to discuss in that sense in more detail. So but first of all, let us look at exercise. Okay, let's look at exercise. So now you look at this one. This one is E1. Okay, we have specified it for you. As I said, in exam we don't give it that way. We don't say this will proceed with E1 mechanism. No, you need to predict it. Later we will look into it. So now you react this with water. So actually, as we said, the Zaitsev Rule apply. So the major product is just going to be similar to this one. Okay, just similar. So this is the product. But okay, E2 and E1, if you look at this common, the strict reaction here, it's just similar with the E2 or E1. Okay, but the mechanism, the difference is the way that it is being, which one is being broken first, which type of bond is being formed first, okay, and so on. So what happened is that, okay, so we are going to just draw for the major product only. It's not that the minor product is not being produced, it's just that I am not showing it, okay, because usually also we ask on the major product alone. Okay, so this one Br, okay, plus water. No, so the step one, I go with step 1. Okay, so the first step is that you see Br here, okay, it already have 3 lone pair actually. So let's say there are 2 electrons here because there are 2 electrons in a single bond, correct? So the first step is that these electrons are going to be transferred to this Br. So it will produce a carbocation here, and it will produce Br minus. Okay, so you are going to have Br minus. Okay, so next one. Okay, what happened? Okay, so the second step, step 2. Okay, so only here where the water will come into picture. So you have it positive plus water. So for water, usually I will just draw it. Okay, so the structure like this. Okay, so this one, okay, remember which one is your beta hydrogen. So this beta carbon, this is beta hydrogen, correct? Beta carbon. So on the beta carbon, you have beta hydrogen, right? Okay, so here what will happen is that there will be a bond formed. It's fine if your arrow is like that, as long as it is curved. Okay, so this electron are going to be used to form bond with the hydrogen. Okay, so what happened is that it is going to form H3O plus hydrogen. Okay, and then you have another hydrogen, so this one is going to be plus. Okay, you can write it as H3O plus, but this one is just for the sake of I want to show it to you so that you can view it clearly. Okay, so and then what will happen is that because the hydrogen want to form bond with the oxygen, this bond must be broken. There are 2 electrons there is being transferred between alpha and beta carbon. Okay, so that is why it is going to form this alkene. Okay, so as you can see, this one, the product is similar to that one. That's why important for you to predict the product first. Okay, so now let us try and look into how do you want to draw the energy diagram. So the energy diagram is going to look like this. Okay, because this is 2-step reaction, correct? Okay, so 2-step. So the first step is going to be this one. Okay, so you just need to draw your reactant Br. Okay, so here it is going to be positive. Okay, why? Because during the transition state, okay, there is bond about to break between the carbon and Br. So this is your transition state. Okay, so next, the second step. Okay, the second step, I just draw it like that. Okay, so in the second step here, you see it is the carbocation react with the water to form the product, which is this one. Okay, so you can write all the product, which and the byproduct H3O plus and also the Br minus. Okay, so at the heel here, the transition state here, you see what is going to form. Okay, so what is going to form is that, okay, there will be a H2O, OH2. Okay, so there is hydrogen. Okay, there is bond about to form. Okay, can you see it? There is bond about to form there, and there is bond about to break between the hydrogen and carbon, and there is a bond that is about to form between the alpha and beta carbon. So that's it. This is going to be the transition state. So you need to make sure you label all the energy diagram, and then all the transition state, okay, and all the activation energy, and also all the enthalpy fraction. Okay, that's it. Okay, so now if you look at this one, predicting the likely mechanism of elimination reaction. So for this one, usually I would like it to use this table only. Okay, so now first of all, it's just like when you look at SN1, SN2, you need to look at the types of alkyl halide first. Okay, the types first. So whether it is primary alkyl halide, secondary or tertiary. Okay, so here when it is primary alkyl halide, we don't care whether the base is strong or weak. We are still going to find it is going to go with E2 mechanism. Okay, but if you look at secondary alkyl halide or tertiary alkyl halide, you have to consider, is the base strong? If the base is strong, okay, it is going to go straight with E2 mechanism. But if the base is weak, okay, the base is weak, it is going to go with E1. If the base is weak, it is going to with the E1 mechanism. So for us, this reaction, usually we need to look more into the base as well. Okay, all right. So like this one, okay, this one, look at this one. This one, what type of alkyl halide is it? That's why I taught you initially, you need to understand what is primary, secondary, tertiary, and so on. So this one, if you look at this one, this is a primary alkyl halide. So why primary? Because you only have one beta carbon. Look at this one, this alpha carbon, this is beta carbon. So one only. So the primary alkyl halide. So this is a strong base. Do you need to know that is it strong or weak? Don't care, because when it is primary alkyl halide, it will straight go to the E2 mechanism. So this reaction will go with E2 mechanism. So what will be the product? Okay, the product is going to be like this. Sorry. Okay, so this is going to be the product. So how do you want to draw the detailed mechanism? You try it on your own, right? Okay, try it first. Okay, so later I will share you the answer. What about this one? Okay, now this one, draw the detailed mechanism. I would like to see you draw for both major and minor. Try it. Okay, so first of all, is it going to go with E2 or E1? Okay, so E2 or E1. Now look at this one first. Okay, this is your alpha carbon. Attached to the alpha carbon is beta carbon, beta carbon, beta carbon. Therefore, this is a tertiary alkyl halide. So, if it is tertiary alkyl halide, you must look at the base, strong or weak. Okay, so now, because this one is a weak base. Remember, it is neutral. It is not an ionic compound. It's covalent compound. Covalent compound, weak. Okay, so covalent compound, weak. So tertiary, weak base. So it is going to go with E1 mechanism. So what is going to be the product? Okay, the product we have actually predict it from this one. Okay, from this one. Okay, major and minor. Okay, if you want to draw for both, you can. If not, you can also draw only one, depend on you. Okay, all right. So that's it. Okay, so you can try to do all of this on your own. So last but not least, let me just brief. I'll just like share you a bit on the alkyne synthesis. Okay, so from the alkyne you can from alkyl halide you can form alkene, and also from alkyl halide you can form alkyne. But if you want to form alkyne, you must have two bromine or two halogen group. Okay, for example, like this. Okay, like this. Okay, you need to have a vicinal dihalide or germinal dihalide. If you still remember, when I talk about alkyne addition reaction, I have discussed this one with you, correct? With the Markovnikov rule and so on, right? So it's just the reverse one. So if you have vicinal dihalide, meaning to say, in the first part, you're going to remove this X and this hydrogen. Okay, so the second part, you remove this X and this hydrogen. Okay, so for you are going to form an alkyne, because when you have this one, you still have your halogen and also the beta hydrogen. So in this case, you can still undergo the elimination reaction. So you are going to form alkyne. Alright, okay. So similar like germinal dihalide. If germinal dihalide, maybe in the first place you remove this one, in the first place you remove this one and this one. The second step you remove this one and this one. So you see, in this one you initially form alkyne, okay, alkene. So but you still have your halogen and also your beta hydrogen. So you are going to form the alkyne. You're going to form another pi bond, so you can form the alkyne. Alright, so that's it. So usually we will use NH2 as the base. Okay, we don't usually use the OH and so on. Right, OH usually we use for the alkene synthesis. But as I said, the alkyne synthesis here not very critical. Okay, so that's it. So this is a summary of this chapter. Okay, so sorry for the E1 and E2. So what is the difference? So this one also you can find it in this what do we call this module, because it's the same thing that I transferred into the lecture notes. Alright, okay guys, that is all. I hope that you are clear by now. What you need to do is just do more exercises. If I have time, I will share you more exercises for you to attempt. As I said, for organic chemistry, if you want to score, you have to do a lot of exercise so that you can understand it better. Okay, first of all, understand it first. Then you do a lot of exercises. Okay? Alright, bye.